Okay, and I'm going to do this recording using Cam Studio. Hopefully this time I have got the right mic connected up, so it's using hyphen mic. Doesn't appear to be a video option on this, but there must be. So I hope I can figure out the video option later on. Let's talk through this work solution. So we're now going to find the reaction points where we have included a uniform distributed load, so UDL. You can tell that we've got UDL because it usually has some sort of like maybe a gate or maybe some sort of solid section there, and you'll see that the magic thing that they're looking for is Newton per meter. Here we've got kilonewton per meter. So once we've got a per meter term, we know that that must be a distributed load. This is a uniform one. And this, of course, we don't do anything more difficult than uniform distributed loads. And certainly in structural analysis, you could go quite far with just that restriction. So to find the reaction points, we need to introduce a temporary measure where we get rid of this uniform distributed load and replace it with a concentrated load. What I like to do is usually do a new diagram where I've removed this and replaced it with the concentrated load. You have to be a bit careful and then switch back to my original diagram for if I wanted to do further analysis. So, and then switch back to my original diagram for if I wanted to do further analysis. So, some people can make the mistake in an exam situation where they replace their distributed load with a concentrated load. They do the maths and then they require to do further analysis, and then they start, believe it or not, the concentrated load and also the distributed load in their further calculations. So it's a good policy to try and separate the two. So let's go through the PowerPoint and see what happens. So the first thing that we want to do is to replace the UDL with a point equivalent to the total load of the UDL. And we're going to replace that point load at the midpoint of the UDL. Remember that this is just going to be a temporary measure in order to help us calculate the reactions at the supports. So we're in effect just going to convert this and go back to the same kind of problem we had for work solution 1. So good plan is to actually just get rid of it and then replace it with a concentrated load. So I've removed it, and I've worked out the mid position of where my UDL is going to appear. So it's a 4 meter long UDL, so half of 4 is 2, so it's going to be 2 meters away from its start position. So that's where people tend to go wrong, is they tend to actually locate the midpoint incorrectly. So that's usually where they go wrong. I haven't seen many people go wrong getting the actual total mass of the UDL incorrect, and most people get that. So all we have to do there is take our UDL, in this particular case we're using kilonewtons, so kilonewtons per meter, and times it by its width, which is a total width of 4 meters. So 20 times 4 equals 80. So that's now going to be our point. So that is now we've just got really the same sort of problem that we had for work solution 1. Right, so notice that I was a bit naughty in my diagram. Well, actually, to be honest, not my diagram. I was a bit, we were lacking one thing, which was we didn't actually define a hinge. Strictly speaking, we should have done. But we know all the forces are going up and down, so this is a bit redundant. We're going to calculate the forces going off in the left to right direction. I'm going to call that positive. I didn't actually label any forces, so all I've got there is 0 equals 0. So there wasn't actually any horizontal forces, so okay, so we just skip that. So the next stage is let's look at the forces in the y direction. I'll define things pointing upwards to be positive, so that's going to be my reactions, so my AY and RBY. Notice how I'm going to arrange my forces. So basically I'm going to go down the beam. So the first reaction I see is a positive reaction going upwards. Next one is a force going downwards. Next one is a force going downwards. Next one is a reaction going upwards. Next one is force going downwards. So working your way across the beam like that, you shouldn't miss any forces as you go along. So there we've got our forces there. They're all on the left hand side and equal 0. So remember what we're saying is, that nothing's accelerating, so my MA bit equals 0. So I'll leave my unknowns on the left hand side as is convention and take my knowns over to the right hand side, and so we've got our first equation. So we're ready to move on and to take moments. We could take moments anywhere here really. So we could have taken moments at A or B. You can see that taking moments at position A is nice because we're now measuring everything from that position. And that kind of relates to the lengths of things, so it's quite easy to use. Also, if we take moments here and go in a clockwise sense, we can see that we can have positive moment, and here we'll have a negative moment, another positive moment. So it's nice to take them there. There's no sort of like. So what I'm saying here is that all the forces are going to be positive moments, while the reaction force here will be a negative moment. So it's to take moments. So as we go through, we have got our first positive force. It's 1 meter from the pivot A, and then I've written this to remind myself that I'm dealing with a UDL, so I've got 80 times by 2 there. Then I've got my negative reaction, and then finally we've got another positive force at the end. So that gives me, there's an error there, which I've actually corrected. So on the original PowerPoint, there you go. So maybe the guy that wrote this was deliberately seeing if you could spot the error. So we've gone from RBY 5 RBY equals 500, which is correct. And oh dear, the B's become an A. So going to substitute equation 2 into 1. Imagine you refuse an exam situation here, you make a mistake. So here's my corrections, you can see, because the font's a bit different. So that should have been RBY is 500 divided by 5. So that gives me 100. And now I'm going to substitute equation 2 into 1. So let's check we're doing this correct, because this is my calculations, I don't trust myself. So 170, take away the 100 from the previous, so the RAY is 70. So finally, let's look at our solution. So we've got a 70 reaction force at A, and we've got 100 reaction force there. Okay, I corrected this diagram as well. So let's just think about it. Does that seem reasonable? So we've got an 80 force acting down here, 50 force acting down here, so we've got 130 sort of pushing down on this section, and then we've got 40, and well, up to that point we've got 40 pushing down in that direction. So it seems like we would be expecting more force to be pushing down on this support than on that support, so it does seem to be the right way round that we've got our reactions. So even though this seems to be well away from the UDL, but we do have 50 pushing down here, which is going to have no effect on this pivot. In fact, it's going to actually relieve that pivot by pushing down on that force there. So it all looks correct.